Hello, everyone. Welcome to M+ Paper Club. So today I'm presenting, and I'm going to present this very new paper that was published a week ago, published as in put on archive a week ago. It's called Quiet-STaR. It's basically an automated way of doing chain of thought prompting without actually prompting manually. But I'll go into the details. We'll have a discussion. The paper is only on archive, so not peer reviewed. I guess we can be the peer reviewers for now. Please interrupt, ask questions. Let's have a discussion. That makes the paper club better, I think. So, okay, to start with this paper, they speak about this only at the end, but essentially it's a way of getting the model uh, to uh, to prompt itself to generate chain of thought kind of uh, responses. Except it's not chain of thought thinking. It's more like you get chain of thoughts for each prompt. Okay, for each token. Sorry, for each generated token, you get a thought. Um, and that's obviously uh, computationally demanding, but we'll talk about those later. Okay? So this is built on top of this fairly large and quickly growing literature of getting LLMs to reason better. And particularly this other paper called STAR. And this one, they call it Quiet-STAR because the thoughts it generates are quiet, as in they're not actively outputted. And again, we'll look at the architecture in a moment. Obviously, there are a number of engineering challenges to make this work efficiently, but also effectively. There are some experiments. We look at the results also. They mentioned those results in the abstract. I think another important thing to mention is that the training is done without task-specific fine-tuning. So they call it actually optimization procedure rather than training, because you optimize the current LLM to also generate thoughts for each token, and you do it on a generic basis, which is the novelty of this paper. And every other similar work that's aimed to improve reasoning abilities of LLMs has been done for specific tasks. So this one is more generic. So you get the LLM to think when necessary before responding, and that's done in a generic way. And then they call it optimization procedure. Okay. Any comments so far? That's the abstract. Okay. Let's go down. Let's start from this figure 1, which is basically the higher level visualization. So I'm going to zoom in a bit more. So this is the training time, right? So you have an original text, and then your LLM generates the next token for each time, right? What we do here is that we allow also generating thoughts between before each next token. Okay? And these thoughts are forward-looking. So you basically you define a reward, which we will look at later. It's a fairly standard reward. You define a reward to optimize a non-myopic thought. Non-myopic means that you want to have a thought that optimizes several future tokens, not just the immediate next one, right? That's also important. And basically, as you can see, they have these little thoughts in between.
What does that exactly mean? Like a thought? Yeah, what is that?
Oh,
so is a thought relevant to more than just the next token. It's relevant for in tokens after that as well. Is that what you mean?
Yes, so that's how it's optimized, right? If you
Okay.
look at examples, I can show they have examples here of thoughts. So if you look at this, so that's some text about magnesium or whatever, and then at some point they have this start of thought. It's a special token which we also optimize, and then you have this extra thought here, which is basically like what you would do if you did these steps as chain of thoughts. Right? You would ask a question, get some response, and then make it go into details when necessary. So here you get this detail speaking about the equation of the reaction that forms magnesium nitride. And this helps for the next bits, right? For the follow-up, for the following parts, to get the equation right. That's what this means. But the way this is generated is that it's generated by to optimize several tokens after this start thought. Okay, that's what they mean by non-myopic. Myopic means you just look at the next token. That was there a question?
Yes, there's a question
Yes.
from me. So, so I'm wondering, so the way it works is that like every time the model is trying to generate a new token, it will previously, like before that, it will generate the entire thought.
Mm-hmm. Actually, not many thoughts. It does parallel thoughts.
Right. Okay.
Yeah.
Yeah, but that must be horribly expensive.
Yeah, the parallel part they can do more efficiently because you can basically use the transformers attention mechanism to do the parallel generation efficiently. But yes, it is horribly expensive.
Yeah.
Wait, I don't think that they do parallel. They do multiple thoughts per token. I thought they did multiple. Like they just figure out how to calculate all the thoughts for all the tokens at the same time.
Yes. Wait, what's the difference?
If you do multiple thoughts per token, then each token will have like 5 thoughts. But if you in parallel compute one thought for all the tokens, then each token will have one thought, but you'll have computed all of them at the same time.
Yes, that's the second. Yes, what do you mean? Yes, the second one. So if you look at this diagram here, right? So you have the text A, B, C, D, and for each A, you do parallel A prime, prime, and so on. And then for B, you also do many parallel Bs. However, this A and B are not they don't see each other, which is done by using this masking, right? So first you have the normal masking. So A, B, C, D can only see the future, but they can also see the future thoughts, right? So A can see A prime, B prime, and so on. However, A prime cannot see B prime, right? So these are masked from each other. But the generation is done like all at once, basically, because it's a transformer. Does this make sense? Cool.
Yep.
Thanks. I just can't see your videos because I'm sharing. It kind of disappeared now. Okay. Back to the high level diagram. Right? I like how they have this cute LM language model robot, and then they have the discarding part. So both about this, by the way. Wait, was there a question?
No, someone just joined.
Okay. So they also have this thing because when you generate multiple parallel thoughts, you also design a reward function to pick the best one. Okay, so this is what they mean here with this discard part. You will basically get the best one. Okay. Spoke about the sampling. Let's talk about the main contributions. Well, they generalized this previous paper, which I think has the same authors, or partly the same authors, to learn reasoning from diverse and structured text data. I mentioned this, that they train the model train a trained model to reason generally across different tasks. And these are their experiments are all zero shot, and there is no fine tuning, okay? Which is to show that they are building a general reasoning ability into an LLM. They do this
But
part
there
of
is fine tuning, but it's not like task specific fine tuning.
yes, not task specific. The fine tuning is this process we mentioned. Like you have to fine tune or train something to generate thoughts. That's the fine tuning, right, Peter? Is that what you mean?
Yeah, yeah.
Just to generate thoughts, yeah. And it's done on a generic data set. Right. We mentioned the parallel sampling, which is basically done taking advantage of the transformer's ability to attend all tokens in parallel at once. They introduced these meta tokens, which also get trained and optimized during the fine tuning process. These are the start thought and end thought tokens. They have this mixing head thing. This basically says don't bluntly take whatever thought came out. Right? You still have a shallow MLP with learnable weights to mix generated thoughts. Well, the results with and without thoughts. Again, we'll see the diagram later. And this loss that looks into the future, we mentioned this also, and the experiments. Right? And then they observed that this approach to get the LLM to think before generating is useful only for the most difficult tasks, which makes sense, right? For the simpler tasks, there is no need for extra thinking. And this can, and then they speak at the end how this can be used to improve the computational inefficiency, because effectively you could have a model that could tell you in advance if you want the model to think or not, right? Because the thinking is the expensive part. So here they didn't do it because it's a harder problem, but as a next step you could do that the decision before generating. We'll speak about this also. Okay, any comments? Cool.
Yeah, I actually think the title of the paper is a bit misleading because the models are not really teaching themselves, so they're not being trained to do anything. It's more like the way that the prompts are shaped, right?
What do you mean they don't teach themselves? What prompts?
Well, it's to me like this approach is like you insert thoughts into the prompt, right?
Oh no, the thoughts are generated by the LLM.
Yeah, no, I get that, but what I mean is, how are they teaching themselves?
Okay, we can talk about that. They use this thing called teacher forcing, which basically means you allow the result to the predicted token to be an input to the model, and that helps the LLM to generate the thought better. Right, so that's what I think. That's what they mean by it teaches itself.
Right.
Because you basically generate the thought and then give it as an input to itself.
That makes sense.
I found this paper a little confusing. So if I say anything wrong or suspicious, please correct me. Yeah. Cool. They talk about related work. There has been quite a bit of work to get LLMs to reason better. They cite a few papers, but the point is they're all for specific tasks. They're all tasks specifically fine-tuned. Right, and then they speak about, well, first the reasoning in LLMs, how they reason, how it's a difficult problem. A few citations that training a language model to reason also related thing, but I think that's okay. So STAR is a self-taught reasoner. That's the other paper, I think, from the same author. They mostly cite here. They introduced the meta tokens. Again, other works have done that before. Peter has done that a lot actually. Remplan also. So it's they cite a few works that have introduced new tokens. But here they also have the token that these tokens are also learnable, right? And they have these start thinking and end thinking tokens. Okay. If you look at the problem statement, they're basically saying we want to optimize a language model. Theta are the parameters of the model. We want to optimize it to have the capacity to generate intermediate thoughts or rationals. They kind of mix and match the terminology across the paper, but it's the same thing. The optimization problem becomes maximizing the expectation over the X are the tokens, right? Over the tokens. So this is the log likelihood of the generated probabilities at each I, right? From to the future, like I to N all the way, given the tokens before that, right? But I is both generated and is an input here, as you can see, it's in both parts. But you also give this rationale, which is the thought, which are the thoughts up until I. Okay, we'll see how these rationales are created.
If the thought is provided after the token, so if
what do you mean
each
after?
thought, what?
No, rationales are for each token until I, right?
Yeah, but so if rationale I is generated off of token I in the sequence before it, then how can it provide additional information about token I?
What do you mean by additional information?
Like I don't understand why that equation, you're trying to maximize the likelihood of I to N instead of I plus 1 to N.
Because you want this I to be here to be an input also. I think that's why they call it teacher forcing. As in, you allow I to be an input here. Right? If you look at the, I think again, I think that's what this. So if you look here, right, these diagonals are not masked out. You actually have access to those. But what's the problem here, Peter?
No, it's okay. I'm still not completely sure, but
they do mention that in theory, in principle, this shouldn't be required because all this information is already present in the LLM. However, in practice, just like chain of thought, it helps the model to extract the information and explicitly, which helps the generation quality. Even though in theory there is no new information, it still helps because it becomes more explicit. That's they mention it somewhere in the text. Is that what you are asking?
I just think that I basically think that you can't optimize, or one of the variables that you're estimating, xi, is one of the inputs to the model.
Yep.
So that means that you know xi. So
yep.
Like you can't if you already know it, then you know the correct answer with probability 1. So there's no way of it shouldn't be in the like as the target.
Let me find that part here. That's another thing they also mention here. Where was that? Yeah, here. I think maybe this is related. On the other hand, when we trained without any interpolation here, updating the mixing head, this mixing head part, right? This is what actually makes a difference. And only using the language model prediction after thoughts, right? The model quickly learned to simply ignore the thoughts. Is this what you are saying? You basically just know what this. And we saw no generalization to any downstream tasks. They kind of have to regularize that. So even though you predict the same thing, you also have to regularize that. And then I'll show how. They have this mixing head thing that combines the predictions. So it's not exactly, it can't be exactly the same.
Okay.
It's kind of weird, I know, but I think that's what they mean. Should we talk about mixing heads?
Let's do it.
Or yeah, let's talk about mixing heads first. So it's define the diagram. Okay, here they have mixers. Those are the mixing heads. They call it. They have a nice mixer diagram. So here is how it works on in more detailed diagram, right? So we saw the high level one. This is a bit more detailed. So you have the tokens A, B, C, D, E, F, and then to generate the next one from F to G, you can either do so the dashed lines indicate tokens are inserted via teacher forcing, right? So this means you have the G that's coming next, but you have the LLM generating the thought from F, and then you also have this thought, right? Right after F, you have the start thought, end thought, and then you have the same LLM also generating the thought in here. And then it goes into this G head, which is then mixed with the LLM's normal generation. So this G head here would be what your LLM would generate normally, right? But then you have this thought here, which is using the teacher forcing thing we spoke about, because it's from F. And then there is this shallow MLP, a mixer that takes the logits, well, not logits, after the softmax values from the two models and learns weights to combine them with a specially designed reward. We'll speak about reward also to generate the next G. So this becomes the G hat, right? And then you have the H hat and so on with the same process. Okay? And they say if you don't have this mixing head, then you can't improve anything because your model just stays here. Its thoughts don't have any impact then.
Where does that G hat, where is that placed? Like it must be put back into the sequence, right? Or no?
I think there's the generated sequence. This is just what you generate next, the next token.
Okay.
Isn't it?
I don't know.
Did they ablate like how far ahead this mechanism is looking?
Yes, they have plots here. Can you find those plots? Maybe up here. Here. So those numbers here. I didn't really understand what baseline here meant, but I'll explain why. So these I think these numbers represent how many. You find it in both plots. X-axis represents training steps. In each line corresponds to a different number of thinking tokens. Right? How many thinking tokens do you have? Like this basically means how far ahead. Is it, or maybe not? Wait, thinking tokens means. Does it mean how far ahead? I think so, right? No, that means how many tokens you have in the thought. No, sorry, this is not what you asked, Amy. This is how long the thought is, actually, not how far ahead you look. Because I think in the experiments they did like 4 only, 3, 4, I think. I thought there was ablation, but I don't think so. No.
I think that'd be a very interesting thing to see if you could like
Yeah.
show, I don't know, 2, 4, 8, 16 tokens ahead and see how that impacts. Because maybe 4 was picked because it was the only one that worked.
Yeah, there was some mention in the appendix also. Let me find that.
If you-
Somewhere
If you
here.
go back,
Yes.
I was going to say, if you go back to the graph, the right-hand image showed the number of look-ahead tokens, I think.
Does it? Oh, maybe I missed that. Here.
You're there. So where you've circled
Oh,
baseline, above that is a series
Oh.
of 4s and 8 and 12.
Oh, there's the one, right? I had tokens.
Yeah.
That's what you mean. Oh, right. That's the one.
Top one
Yes.
is 24, the way I'm reading it, 24 thoughts,
Yeah.
12 tokens ahead.
Yeah, exactly. So they do, yes, thanks, Dwayne. They do 24 tokens for the thought, and then look ahead is 12. Yes, thanks. Cool. As you can see, with more training steps, well, they have two data sets for evaluations. Usually, with more training, performance gets better and larger thought and more token heads usually means better, but until you start overfitting here, I guess. And we call it overfitting. But anyway, at some point, the performance starts going down, or at least plateauing. What I didn't understand is that why isn't baseline a straight line, right? Because if it's baseline, there is no training. So I'm not sure what baseline means here. So maybe it's not baseline as in no thoughts. Maybe that means like 4 thoughts and 4 tokens or and 1 token ahead or something. Right? I didn't really see what
It says
here.
the baseline is a model that's trained on the same model on the same data set without thought tokens.
So why is it not a straight line? There is no training there, right?
No, it's trained. So it's trained in the same
It's
way as the other one.
fine-tuned. I see. It's like normal fine-tuning them on the new data set, right?
So they don't really have a baseline. Or they have it, that's a baseline,
Yeah.
but that's only to show whether the value of different techniques that they introduce in their own method. But they're
Yeah.
not like comparing it to STAR or one of the other previous methods. Maybe it's hard to do that given their method.
They do have a table here. One moment. There should be a table with more numbers. I need to find that. There is a table with more results, I think. Maybe not. I thought there was a table. No. There's no table, yeah? They have lots of qualitative examples, but not table. That's actually funny, right? Normally you would see a table. Maybe in the appendix. This is the same plot, but normalized according to compute. Obviously, maybe this is interesting. They did this plot to show that baseline is so much cheaper because it's normalized according to compute. The others take so much longer to run, right? It's not just this is not just the training steps, but also time-wise, right? So they take more compute requirements. It takes a lot more compute to train these models. But no, there is no table with comparisons.
I'm really curious how this compares to the regular chain of thought, because the idea is very similar, right? It's you're trying to elicit the information from the model, make it more like explicit about what it's doing.
But how much can you systematically do to chain of thought? Because you need to actively prompt it, right?
Yeah.
And choose when to do it as a human. There is a lot of human input there. I guess the whole point is that there is no need for the human to think and ask questions and do the prompting.
No, I mean like repeat the same thing, but with like think step by step and then include the answer before the final answer.
Mm. Ah, you mean just the initial one initial prompt?
Yeah.
Mm. Yeah. Yeah, that would be useful. Yeah. Probably we'll see all these come out as they submit it to a conference. Oh, we want to talk about the reward. Let's go back talk about the reward. That's also useful, I think. Let's talk about parallel generation, mixing heads. They introduced these two start of thought and end of thought tokens, which are also trained, but they are also weighted during the optimization process. They have their own hyperparameter to weight it, to weight the gradient, because they trained it a bit differently, right? So I mean, we spoke about non-myopic scoring and teacher forcing. These are techniques they use. All right, the objective. So they have this reward here, which is basically saying you take the average. So you take the average across all rationals, right? So because you generate many of them in parallel. So the one on the right side is the average. The p bar is the average. Average log probabilities. And then here you have the current one, right? And then you want and then you put this reward as a reinforce objective. So it becomes reward times the probability of log likelihood of generating the right token until after start of thought, right? And then this becomes part of the loss function. Okay, and you use this reward function to encourage keeping thoughts that are better than average. Okay, and yeah, that's the addition to the training loss. You also have the usual log likelihood loss. By the way, you don't just do this, right? You add them. Okay. This diagram is to show that the improvement in loss is skewed towards toward so if you look only at the easy tasks, there is rarely any improvement. But as the original token prediction loss is higher, you get higher improvement, right? That's what this skewness means, showing that this thinking helps only for the most difficult problems. Okay. Yeah, they use Mistral 7B, and they also speak about they could use a better model, and there is work showing that larger models benefit more from improved reasoning techniques. Okay, a few examples here. They highlight I think green means improvements, right? They highlight how generation improves, but I found this a little bit annoying to read this sort of outputs. I would much rather have a table summarizing the results, right? They do show that there is improvement. Performance goes from 5.9% to 8.1% on this GSM 8K dataset. There is another question answering dataset which also improves performance. So there is no table, but they do mention that improvements in on benchmarks. All right. So we trained Mistral 7B with 16 tokens and 4 true tokens ahead. Right. So that's this is for the other experiment, but I think they have a similar setup for the other for all experiments. Any comments here?
So I think that there's two things that I'm thinking. These are more general thoughts based on this paper. One, which is related, well, one is this interesting idea that like basically, or actually it's the key idea here, which I think is really interesting. It's like LLMs have a lot of latent information in them. And if you're doing a forward pass, if you have like a perfect model, they should be able to extract and use all that latent information, but they can't. So that's why you have to force them to generate it and then use it as part of the tokens.
Yep.
And so I'm thinking like, oh, that's really cool. Like, first of all, that there's it basically means that we haven't really tapped the potential of LLMs yet, because we haven't figured out how to get an LLM to use all of its latent information when it's trying to generate text in a good way. And it also makes me wonder, is this the most effective way, or should we be doing something in its latent space, like in its embedding space, as opposed to making it so explicit?
How would you do it in the latent space?
I have no idea, but at the same time, I feel like if you give enough ML researchers a problem, then they come up with an intelligent solution, even if it's an impossible problem.
Yeah.
Yep.
Yeah, that's a good point, but I don't know what to do with the latent space. Yeah, I don't know. I have no ideas about that.
Insert the similar mixing heads, but just instead of having the heads kind of like mix the stuff inside,
Yeah.
or like
Oh,
allow the LLM to generate more than one token at a time.
Well, that's kind of similar to what they do here, right?
Yes, but like not from the perspective of the middle parts of the LLM. Right.
So in my opinion, this form of this approach is what, like, I put it under the idea of like metacognition, where you like think about the task instead of trying to accomplish the task. Like, you take a step back and think about it. So maybe you would try to perform some kind of latent metacognition, like change the architecture so that you're doing this type of, there's some kind of operation which mimics this thought process internally.
I think they do speak about that. Sorry, go ahead, Dwayne.
I was going to say I did some entity salience. So entity salience is named entities in articles that if you remove them, they remove the meaning. So what are the most important ones? And so if you could skip ahead and somehow find which are, rather than tokens, which tokens are important, which is, the named entities in the next 30, 40, 50 tokens, then you can start reasoning about those. But exactly as you're saying, how you do this, I don't know. But skipping all and then sometimes the relationships between the entities is more interesting than the actual entities. So yeah, that's the argument the other way. But just a thought.
So I just thinking about that paper. So we saw this paper at NPlan. We didn't do it at NPlan, but we found it recently. It was accepted into ICLR this year, and it's treating an LLM as an autoencoder. So you like take a large amount of text, you embed it in a much smaller number of tokens. So maybe you have text that's like 8,000 tokens, and you embed it in 1,000 tokens by putting it through the LLM and taking the last 1,000 tokens. And then you use that as the input to a model with a question. Like, you could ask a question about the book, and it answers a question about that book correctly. So that's a way of like summarizing information in the embedding space. So maybe you could do something like incorporate a lot of different, I'll post it, I'll go find it. You could incorporating a lot of different information as like different sets of embeddings. So you could have like one book and 1,000 tokens, and then another 1,000 tokens of another book, and then, but that's not exactly metacognition, but it is a way to introduce ideas without in embedding space without having to describe them explicitly.
They do also mention here, maybe more about Dwayne's comment, but they do mention that in theory we could move this mixer head earlier to predict which token would be more useful here. But that's a much harder task, right? Because you have to predict before generating anything. And then maybe you can predict what to generate next. And then that could be a way to improve the generation. But that's like future work idea. Cool. Should we talk about the last bits? I give some more examples here, but I'm not sure if it's very. I don't really like reading the outputs from an LLM as an example because they don't explicitly say these are not cherry picked. At least they could say that, right? So maybe they are cherry picked. So that's I guess also cherry picking is a good thing here because they do say that this help only for the most difficult tasks. So they do want to show the examples that are otherwise difficult to solve. So maybe that's okay. We spoke about chain of thought, some limitations. We spoke about computational complexity. They also say that maybe it's a good thing. This is actually funny. They are saying, what if you have additional compute, and then this is a way to use it for better generation? Like that's a funny way to look at things, right? But it's more of a limitation, obviously. Yeah, we mentioned about moving the mixing head earlier. Oh, they are saying that we could do things like have an ensemble thoughts, right? Generate ensemble thoughts and choose from them. Ensembles usually improve performance for however you use them. About ethics, this is actually interesting because they do say that there are no safeguards or any sort of controls about the thoughts. Plus, we can't assume that these thoughts are in any way a representation of what's happening underneath the how model generates the next tokens. Right? These thoughts are not an explanation of predictor of the next tokens. So we can't use this as an explanation mechanism, which is probably useful, right? Because when you say thinking before, if you think about a person, like if someone thinks before answering, in some ways that thinking and answering can explain each other. They're saying that we can't make such assumptions here. I think that's all. Any further comments?
I think it's also a massive security risk, like, because it would be such an insidious attack to like introduce some thoughts. So like, I guess you could potentially even like add them to your initial prompts, and then there's no, if this system is working, then obviously it's not going to show the thoughts because that's not how it's been designed to do, to generate things. So
but you don't know.
You could potentially introduce, yeah, like you wouldn't know.
Okay. Cool. Then we can finish here. If there are any other comments, this is a good time. Cool. Thanks all.
Thanks, Vahan. That was really cool. And thanks everyone for coming to Paper Club. We'll see you next week, hopefully. Bye.
See you next week.
Thanks.